Before I dive in too far,
This is such a fun novel.
any questions coming up on the homework at this point? Since it's been posted for all 24 hours, everybody's got quite a bit of it. Yeah.
I'm just wondering why there's like the chapter 7 questions on it.
There's a couple volume questions that then involve like integration by parts or some of the other techniques that we've already learned. And so, yeah, so I think they're both volume questions, but they're integrals beyond like polynomials. So I don't think they'll be like super awful. Any other questions? Concerns? I did this morning delete the 6.5 homework. We'll do 6.5, but we won't get there till Friday, and that's not enough time to do homework. So we'll put it on next week's homework. Okay. All right. And the tests are moving along, but not there yet. Okay. And we need to practice integration. Okay. Yesterday we did a bunch of stuff with springs. Remember, our general idea with work is force times distance, but in the problems we're doing, these are variable quantities. They're going to be different as we move through the system. So, of what's going on. And so, today we got a couple different types of problems here. First thing is kind of like rope problems. So, we have a rope 50 feet long. It weighs half a pound per foot. Edge. High. Work is done. Pulling the rope to the top of the building at a constant rate. Honestly, the worst part about teaching this section is like having to write these problems up on the board. Okay. I get to draw pictures. That's great. That building is 120 feet tall. And it's a boring rectangular building. Sorry. Instead of, I don't know, something more interesting. Anyway. We've got a rope hanging down. It's 50 feet long, so it doesn't even quite hang down halfway. and we're gonna pull that rope up to the top. So, this time, if you will, in some ways the force is what's variable. So with rope problems, we can think about it two ways. Okay. Maybe not. Maybe it's the same thing. But part of the idea is that as I pull the rope to the top, there's less rope to pull up, right? And so after I pull 2 feet of the rope, then I've got a pound less to deal with. And so now my force is a little bit smaller. Okay. So does that make sense? Okay. So we have to kind of identify 2 things. And so the way we cut this up, I might be able to get together today, is like we sort of cut up little small segments of the rope. For each here, say 1 foot segments of the rope. And I know the mass of that's 1/2 a pound, but then I have to figure out how far it goes. Okay, so I guess, yeah. So that feels like I'm describing 2 different things. Anyway, so here's how it goes. If we think about, say, the rope right here, okay? One of the things we have to do is we have to put a scale on this, okay? I need to know where that rope is on the scale. I know my scale goes 0 to 50, but does 0 start at the bottom or does 0 start at the top? And while the formulas and things look a little bit different depending on which side you do, it doesn't really matter which one you do, okay? But you have to write the right formulas for which one you're doing. Does that make sense? Let's put 0 here. On my scale, it's going to go 0 to there. And so, right here is some x value. Okay, or if you want a different letter, that's fine. But I've got to think about how much weight does my segment have, okay, and then how far does it need to move. So for me, when I do this, I'm sort of figuring out 2 things. I'm figuring out the force and I'm figuring out the distance. I assume that somewhere along the line there I'll have a dx, okay? And yeah, and then I put that together and when I do the integral, right? I'm going to multiply the 2 when I do the integral, okay?
Does the 120 matter except that it's longer than 50 feet?
It does not. Good job. Yeah, except that it's longer than 50 feet, so none of this is sitting on the ground. Okay? So if I take a little segment that's right here, I need to know how much does it weigh. Okay? And the answer is, well, it weighs 1/2 pound for every foot that it is. So I need to know how long the segment is. Okay, that's my dx, right? That's my delta x. And then times 0.5. So the force that I have here is 0.5 dx. Everybody on board with that? Mm-hmm. Okay, and then how far does that segment move? Well, it's got to move from position x to position 0. So that's x feet, right? Okay, and every segment starting at 0 and ending at 50 needs to move that way because I'm pulling the whole rope up. So my integral will be 0.5x dx going from 0 to 50. I'll just go ahead and erase the 120 feet since it doesn't matter and it's in the way. Any questions about the setup there? Then we integrate. 0.5 is 1/2. When I integrate x, I get 1/2 x squared, so I'm going to have 1/4 x squared overall, going to 0 to 50. 50 squared is 2,500 divided by 4. That does go in evenly because that's multiple 25. I think it's 625. And then we were dealing things with feet and pounds, so that would be foot pounds. All right, any questions on that? Yeah, there's some part of me that feels like there's another way you can do this, where like the weight ends up being, like the whole rope is 25, and so you do like 25 minus 0.5 dx or something like that. But then I can't remember how to get the distance right there. Yeah, I don't remember how to get the distance right. Anyway, that one worked, so let's do that. Sound good? Okay. That's really gonna bother me like all day, I'm sure. God, there's another way to do this. I might have to do it the other way. Okay. I think it's gonna be worth having you guys try one again. Okay. No, here's the big question. Should I just preempt the question you're going to ask me on homework? The assignments I gave you, I'm so done. Oh yeah, I'm running on double sleep here, so.
Is it number 20 or 15 on 6.3?
I was looking at number 19 on 6.4. I have a suggested problem, but I think we should try that. Here's the worst it can get. Should we do that? Well, we should not do this one yet. We should do a normal one first.
Okay.
No, and here's my thought is like you're not gonna be able to do it. Maybe you would. Sorry, I feel like that's insulting. The problem is you're doing this with a rope, but you're bringing up a leaking bucket. So you have a weight in the bucket, but it's leaking and getting smaller as well. Okay, now, do you want to try that on your own?
Well, you need two integrals in that one.
Okay, great.
You could, but I'm assuming the problem.
That's the one I just did.
Oh, yeah. Well, no, the weight's not gonna be constant. That's why I need two integrals. There's more rope you pull up, there's less rope hanging down.
Okay.
Which reduces force. It looks like the rope's different too, so it's slowly losing mass as well. Really keep bugging trying to put up the fire.
A 200-pound cable. Sorry for all your SI fans here. These is 100 feet long. Vertically on the tall building. How much work is required to raise it to the top? What's that? The weight's not the same. The weight density is a little different. Yeah.
Is the building taller than the cable?
Yeah, it's tall enough that the whole cable's not hanging out. Okay, concerns? We'll come back to the leaky bug problem. I wanna make sure we have enough time to do tanks. Okay, and then we'll come back, and don't know that I'll necessarily take that one, I just wanna make sure we have time to do a good job with things. Okay. So I'll prioritize it first and then we can do it. But like what would happen if on this rope I had, you know, a 50-pound weight that I was pulling up as well, whatever it was.
So let's use that.
Yeah, I just really have to add 50, right? And in fact, I could totally do that separately because I'm just, now the weight is constant and the distance is constant, right? And so it's just 50 times 100. For the amount of work that adds. Does that make sense? Okay. What if the rope is on the ground? What if some of the rope is on the ground? It's more like that just becomes a dead weight that I have to lift the entire distance. Does that make sense?
Yeah.
So if I've got 10 feet of the rope laying on the ground, then
You just multiply how much it weighs.
I take, in this case, it would be 10 times 2. I've got this 20-pound weight that has to travel the entire distance. Okay. Does that kind of make sense? Okay. So, I mean, there's some differences. There's some other things in the probe cuts. Yeah, I was obviously just looking at problems where they're like just taking the bottom end and lifting it up, and that would work a little bit differently. We'd have to think that one through. How much is each piece sort of moving? But anyway, okay. Let's do some water tanks and see how that goes. So, and then we can do the leak bucket. Sounds kind of fun. Why can't Jay do it? I don't know how that would go. That would be an interesting. I know, but I can't come in tomorrow, so. Like that would be an interesting. Okay. All right. So here's the. We should appropriately call this the water tank problem. So let's do this by example. Find the work done in emptying. The following. And why do I have everything in feet? Oh well. Should we make this not feet? Let's make this not feet. With water. It doesn't matter because on my notes I don't have any answers anyway, so you know, might as well. So our tank looks like this. That's not my bad drawing. It is supposed to be the bigger one on top and then the smaller one on bottom. Okay. The top one we'll say is 6 meters, and the bottom.
Is that radius or diameter?
What's that?
Is that 6 meter radius or diameter?
That is a radius. The bottom one has an 3 meter radius, and then the tank is 8 meters tall. I'll move out of the way there, sorry. Oh, also, another thing that's important is we're emptying it through a spigot that's at the top of the tank.
How does that work?
What's that? I'm pumping it, I'm pumping the water up right now. Okay, it's a work problem, so I need to know an amount of force, and I need to know a distance.
Yeah.
Okay, and what's the force that's really going on here?
Water?
It's like
The weight of the water?
the weight of the water, right? So I need to know the weight of the water. Okay, so we need a fact here that's important that at some point I had memorized, and today's not today. We need a density of water. One gram per milliliter. Right, so the density of water is, I think it's a kilogram per liter, right?
Yeah.
Yeah.
Probably.
Okay, cause that's more the scale we're dealing with here. But what we really want that in is not liters, cause we're gonna end up calculating a volume here, not in liters, we're gonna calculate it in cubic meters. Okay, so we need to go there, so I'm pretty sure that it's 1,000.
Yes.
Is that sounding right? 1,000
Kilograms.
1,000 kilograms per cubic meter. Let's get a look and make sure. Okay. Where does it have those? I know it has Yeah, thousands right. I'm trying to remember. Okay, so somewhere else in your notes, you might wanna put this one. The density of water is also in US units. And they have this in the problem that, in like number 20 has this fact written down. But it is, it's 62.5 pounds per cubic foot. Okay. So this is, this is kind of an aside fact, but it's super helpful here, right? We need to know those densities in order to be able to do problems with tanks. Okay? So the way we do this, again, the calculus theory behind this is that we think about taking a small slice of water and we think about this disc or cylinder, okay? And we'll take that much water and we'll lift it up to there. And so the water has it has a mass, but we're really more concerned with the force. So the weight of that water, and we can compute that because it's volume times density, star there for a second, but we can compute the weight of the water there by knowing the volume of the slice that we're taking, and then its position tells us how far we have to lift it. Okay, so again, I set this up in the same sort of way that I showed you here, where I sort of separate the force and the distance. Okay, just to kind of guide my thinking. So here, force it's our density. We have D too many times. So I think sometimes they start doing a delta there for density, because I'm going to use D for distance, right? And then I also have dx. So I've got too many D's floating around, so we're just grabbing another letter here. And so delta kind of is like D, and so great, we'll use that for density for right now. Okay, times volume is our force here, but in the case of using SI units, our density, notice, is given in mass, right? It's kilograms per meter squared. It's not newtons per meter squared. And so we also have to multiply by gravity. And G is what we use for the gravitational constant. Well, not constant in this case, the acceleration due to gravity. Okay, So, before we go further, any questions about that? Okay, do we need to do the G if we're using these units? No, okay. And so I have seen before, I'm not looking super closely right now and seeing it, but I've seen them use two different formulas for this then. One where we have like, I don't remember which one gets the delta and which one doesn't. But one of them where we have G times delta times V, and then they have a different formula where it's they use a different letter for a force density, or for a weight density than they do for a mass density. And so if you're looking at two different things, that's the difference, okay? Is one of them has, I mean, those two pieces separate, one of them has the same. Okay, because I know you all, thoroughly read the text.
For sure.
Yeah. Math books are such a great read. You didn't hear that from me. Anyway, all right, so we've got, 9.8 for our mass density. So for the acceleration of gravity, and then 1,000 kilograms per cubic meter. For our density. And now we need to figure out what the volume is. Okay. Again, we're gonna have this variable x in here somewhere that's gonna somehow represent a distance or something like that. And so again, we need to sort of set up a scale on this. Where is x equal to 0? Where is x equal to something else, right? Because it's not naturally on the x and y plane. That's why. Okay. Again, it doesn't necessarily matter. Things look a little bit differently depending on where you put 0, but it's correct to do the problem either way, as long as you get the correct expressions along the way. So, I don't know. I often like to put 0 up at the top where I'm doing this. There's a couple schools of thought on that, but and so the bottom here would be x equals 8. Okay. The nice thing is that gives me my distance is just x, right? Wherever I am, that's how far I need to move. Okay. But can you tell we're gonna have to work a little bit for this? So if this is at position x, the shape of the cross section, or the shape of this is it's a cylinder, it's a disc. I got to do the area of a circle times dx. That's where my dx is going to come in, is in this thickness here of this shape. And the radius is changing as I move up and down the tank in this case, right? Okay, so I have to do a little bit of work to figure out the radius. Okay, I can sort of abbreviate this at this point by saying, hey, look, I know this is pi r squared times dx. Okay, because that's the area of a circle. I don't know what the radius is yet. I'm gonna have to work a little bit harder at that. Okay. So again, there's a few schools of thought on how to do this. I find it easier just to write the equation of a line. The radius, at least in this shape, is changing in a linear way. Okay, and what I have is when x equals 0, r equals 6. So that was the top, right? And then when x equals 8, that's the bottom of my tank, r equals 3. And so I've kind of got x and y coordinates, if you will. They're x and r coordinates, but I can write the equation for a line now. Okay, I have 2 coordinate points. I can write the equation for a line. So you remember doing that way back in the day, and you probably did that several years in a row, where it was like, here's 2 points, find the equation of the line between them. We're doing it again in the context of this problem. Okay, so we'll do 6 minus 3 over 0 minus 8, and that equals 3 over negative 8, so negative 3/8 is our slope. y-intercept's easy, or it's the r-intercept in this case, it's 6. So our radius is 6 minus 3/8 x. Or negative 3/8 x plus 6. Okay, any questions about that process? Okay. So our force then is 0.98 times 1,000 times pi times then 6 minus 3/8 x squared dx. Okay, so as an integral then, I've got to do force times distance. So I'm going to have 9.8 times 1,000 times pi times 6 minus 3/8 x squared, and then distance x, and then I'll have my dx. And that's going to run as an integral from 0 to 8. Now I can simplify life a little bit, not a whole lot. And we're also going to need to expand. But we can pull all the constants out. And we don't need to write 9.8 times 1,000 forever, right? We can go ahead and multiply those and get 9,800. So we got 9,800 pi times the integral of 0 to 8. Let's expand. We'll get 36 minus, let's see, 6 times 3/8 is 9/4, and double that, it's 9/2 x, and then plus 9 over 64 x squared, but that's still all multiplied by x dx, and so we do integration by parts. If we want to make our lives miserable and do the really long way, or we do the simple way and just multiply x through, and the power rule. Okay, I can integrate now. I'll have 9,800 times pi times, let's see, this would be x squared over 2 times 36, so 18 x squared, minus 9/2 x to the, well, so we'd have x to the third divided by 3 times 9/2, so I think we'd end up with 3/2 there, x to the third, and then plus, this one just gets worse. I need 64 times 4, 6 carry 1, 256. All that evaluated from 0 to 8. Having 8 in there will clean up our fractions quite nicely. Forgive me for not wanting to do this on the board, but so insert calculator at this point. When we plug in 0, we zero everything out in there, so we just have 9,800 pi times all that with 8 in for x. Yeah.
So I'm just confused as to where the x dx came from, because in our force equation, we don't have
Okay,
x dx.
no, so the dx is coming from the force.
Okay.
The x is coming from the
Oh, the
distance.
distance. Gotcha, thank you.
And I just kind of shoved it in there so it's not after the dx. So I like my dx last in my integral. Yeah.
This will be a silly question, but for the r, where did the 6 come from?
What's that?
For the radius, where did the 6 come from?
I'm essentially doing slope-intercept form,
Oh, okay.
right? So here's my slope. There's my y-intercept.
Oh, okay.
Right, when x equals 0,
yeah.
that's the y-intercept. Magic, it came from magic. Yeah. No, just kidding. That was the y-intercept. Okay, and then, yeah, you can get approximately. I'm okay if you leave this in terms of pi, but if you don't, It's meaningless to me either way. Sorry, I don't know how much force, 2,000 newtons is, so. It's just a bunch of newtons, and okay, that's great, but. So leave it in terms of pi, round it off, that's fine, I don't care. At the scale we're dealing with, we probably don't need any decimals.
Extract the additional number.
I mean, like, does that make sense? I don't care if there's an extra half a newton. If I'm dealing with 15,000 or something like that, who cares? Anybody have a number?
528,
So,
or for the parentheses.
okay, for in the parentheses?
Sorry,
No, that's fine, what is it?
I was to say the whole number then, because I was like, sorry, I should just give you that.
Okay, so which one are you giving me?
The whole thing, I guess.
The whole thing? That's fine.
5,174,400. 7 instead of 2.
What's that?
This is 7 instead of
5,174. Okay. So I really just need to erase that little extra part there. Okay. Are other people getting that as well? Okay.
2. Oh, yeah.
Right, and like, do you get it? Like, those two digits, whether or not they round to 0, 0, it probably doesn't matter. We're dealing with 5 million units.
Should we put pi in that too, or do you just?
Is that with the
Yeah,
pi already
sorry.
multiplied in, or is that times
That's
pi still?
with pi.
That's still times pi. Okay, I misunderstood that. That's my fault. Yeah, so 15 million,
A lot.
0.3. Just kidding. Okay. Cool. Question about setting up that tank problem. Okay, can I make you aware of a couple changes that might happen in doing problems? Number one, we might be emptying it out higher than the tank is.
So the distance would just be greater.
Yeah, what if I'm pumping it up through something that's a meter or two above at the end of the tank? Then my distance has a +1 or +2. Okay. The other option is maybe the tank isn't full. Okay. And if I set it up this exact same way and the tank isn't full, what happens? Maybe my tank's, down here, that's where the water level starts. Well, then I don't integrate from 0 to 8, I integrate from wherever the water level is to 8. Okay? Does that make sense? Okay, in setting these problems up, I see there's like 3 or 4 possible places to put 0 that sort of makes sense. Okay, one is what we did at the top of the tank. One is at the top of the water, which is also what we did because they coincided this time. Okay, one is where the spout is, which we also did because that coincided with everything else this time. Okay, and then the other one is at the bottom. And I feel like those are the ones that make the most sense for 0. The one exception to that is if I have a spherical tank, to deal with the radius, I probably want 0 right in the center. Right, and sort of put that on an XY coordinate plane centered at 0. And then it works out a lot nicer. Okay, does that make sense? But those are some variations, and so I do want you to take a look at the homework and bring in some questions tomorrow or Friday. Friday you should have your test back. I only have 2 pages left to grade, so even if I only grade 1 page a day, by Friday I'll be done. Yeah. The bags under my eyes might be really deep, but that's it. We didn't have time to really talk about the problem, so maybe tomorrow. We'll give Jay a crack at it. If that happens. I think, just for this, even if this isn't the most realistic way, even if a physicist is gonna be like, oh, there's a much easier way to do this, and here's what it is, I sort of like this thinking process that goes on. To me, that makes the problem a little bit more enjoyable, though it does make it a little tumultuous. But sort of thinking all the steps through. Yeah.
Okay.